So videos are going to be even better than before, right? All right, so let's talk about some of the mathematical tools that we need to have mastered before we start doing some analysis of algorithm. Start with some basics. So one of the things that we want to learn is we want to learn a couple of functions. One is called floor, and one is called ceiling. Another name for floor is the greatest integer function. You guys are familiar with greatest integer? No. Okay, so the parameter inside the greatest integer function, which is also known as the floor, is any real number, but the value is always an integer. So what it does effectively is truncate the decimal. So bring it, so for example, the floor of 2.99 is 2. The floor of 2.01 is 2. The floor of 2 is 2 because 2 is an integer. So if it's an integer, how about the floor of negative 3? Negative 3 is 3. Is negative 3. Yeah, negative 3, sorry. And what's the floor of negative 3.1?
4. Negative 4.
Negative 4.
3.
Because the rule is the greatest integer less than or equal to the number. Now if the number is an integer, that's it. But if it's not an integer, then it's the greatest integer less than the number. So that's why negative 3.1 less than the number is negative 4. Does that make sense? That's the greatest integer function. Sometimes we call this the floor. We bring it down, right? Bring it back. Bring it back to the left of the number line. So anything in the middle of two numbers goes back. 1.5 goes to 1. Negative 2.5 goes to negative 3. Because it goes to the left. Okay, now the other function is called the ceiling function, and it works just the opposite. So it's the smallest integer greater than or equal to the number. So if the number is an integer, it's the value. But if the number is up in between, it goes up. So it just goes the other direction as the floor. So that's very, very straightforward. Okay, now the other type of functions that are important for us are going to be logarithmic functions. So the function y is equal to natural log of x looks like this, right? Do you know what I mean by domain? Domain of a function?
Range? Range?
The range is what comes out. Domain is what goes in. Set of inputs. So if you look at this function, what our x values can be? What happens to this function natural log of x as we get closer to 0? It goes basically down, 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 down. It never gets to, so 0 is not in the domain. But any number greater than 0 is in the domain. So the natural log is defined only for positive real numbers. And that's what it looks like. So you can see that the function it's growing. It's always increasing, right? We call this strictly increasing. Strictly increasing. Strictly increasing means that if x is bigger than y, then log of x is bigger than log of y. So strictly increasing. As we go to the right, the function is increasing in value. Okay, now, so that's the natural log function. Now, the natural log function has been defined as, and this is important, the integral of 1 over x dx. So let's talk about that a little bit. I'll be talking a little bit about integrals today in some detail about the interpretation. Essentially what we're doing is the integral is sometimes interpreted as the area under a curve. The area under a curve is the integral. So it's the sum of the areas. Sum of the areas. And there are two ways of computing the sum of the areas. One of them is a discrete technique, and the other one is a continuous technique. So they're both summing areas. Sum, sum, sum. So therefore, I'll just show you an idea. Let's get this thing up a little bit. So suppose we have a value here. So this is 1, 1, 2, 3, 4, right? So what we're going to do is what is the area of that rectangle? I know it looks funny, but it's actually a square, isn't it? Because that's 1. So the area is? It's 1. You want me to make it more realistic looking? I have to make this. Okay. So now, where do you think this is? It's what, half, right? What's the area of this? No. What's the width of this?
1.
And the height?
0.5.
So therefore the area is a half. So this is 1, this is 1/2. So now, guess where this is going to be? 1/3. I'm doing 1 over n. 1 over 1 is 1, 1 over 2 is 1/2, 1 over 3 is 1/3, and then 1 over 4, and it continues like this, right? So what is the area of these rectangles? Well, the area is going to be 1 plus 1/2 plus 1/3 plus 1/4, right? And if I continue, plus 1/5, etc., depending how many of the terms I have. Now, why is this always equal to 1? Because basically, if you go from 0 to 1, the width of this rectangle is 1, and the height is also 1 because I stopped it there. From 1 to 2, the width is 1. From 2 to 3, the width is 1. So basically, it's always going to be 1 times the height will give you the area. Right? Now, so that's the function 1 over n, and we call this a discrete function. Discrete function. Discrete functions are the functions defined only for what? What type of numbers? Integers. Integers. So discrete functions work on integers. Now I could have another function, I'm going to call it 1 over x. Looks the same, right? Because x is a variable, n is a variable, but I'm going to call this function continuous. If it's continuous, then basically when the value is equal to 1, it's also equal to 1. Because 1 over 1 is 1, it's continuous. So every single point is going to have its own point. It doesn't have discreteness as going across every integer. So the value at 2 is going to be what? 1/2. The value at 3 is going to be what? 1/3 and 1/4. Now what happens between those values? So for example, what happens at 1/2? It's actually going to be 2. Which is going to be someplace up here. So this is 1, this is going to be 2. So 1/2 is going to be about here, right? So the function looks like this, right? And like this, and like this, and like this. Are you with me? So essentially, this function is continuous, but the area under the curve looks like it's, if you go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, it looks like the area under the curve here is actually bigger for the continuous function than it is for the discrete function. You see what I'm saying? So for example, let's say I wanted to compute the area of the rectangles, but there was no rule or no formula to do it. It was not something that we could solve analytically or mathematically. But there was a way to find the area under the curve, which was similar to this one. In fact, if I wanted to find, for example, the summation as I goes from 1, let's say, to some value k of 1 over n. Now, that has a particular value, right? Unfortunately, there's no closed form for that summation. But we could say that if we look at so from 1 to n. Now, if I start at 1 over here, notice that the area from 1 to 2 is actually bigger than the area from 1 to 2 here. Right? And the area, the continuous area from 2 to 3 is bigger than from 2 to 3, the discrete rectangle. So therefore, what we can say is this is going to be less than or equal to the area, which is the integral, which is the continuous area under the curve of the same continuous function, as we go from 1 to 1 of 1 over x, and then as x gets as the differences between x and the next x get smaller, we use dx, which means that it's the limit of x as x goes to 0, as the number of x's goes to infinity. Okay, so what we have here is we have an infinite set of points. In order to get the area from here to here, our integral has to go from 1 to 2. But our discrete is only 1. So in order for our area to go, let's say we want to find out from 1 to 4, that area is going to be, well, let's go 1 to 3. Let's make it a little bit easier for ourselves. 1 to 3. Then the discrete area is going to be here, right?
Yeah.
1 to 2, 2 to 3. No.
1. The 1 before.
1 to 3, so it's 1. Oh, sorry, so it's going to be here. Right. Okay? But if we look at the area, of the continuous one, if we start, where would we have to start from? Do we start from 1? If we start from 1, then our area is already smaller. Meaning the area from 1 to 2, from 1 to 2 here is smaller than the discrete area from 0 to 1. You follow what I'm saying? So what we have to do is we have to start not from 1, but from 0. And how many boxes are counting here? How many boxes? 3. 1, 2, 3. When we go from 0 to 1, how many boxes do we have?
1.
Not boxes, but you know, the continuous. And then so we have to do a second one and a third one, so we have to go 0, 2, 3. Are you with me? So what I'm showing you is we don't know what this summation is exactly, but we know this summation is less than or equal to the integral of the same but continuous function. Notice that our limit on the integral is 1 less, but our limit on the top is the same. So if I can solve this, and I can solve this, and the reason I can solve it is because by definition, the integral of 1 over x dx is natural log of x. So this is equal to natural log of x, and then because we're going from 3 to 0, 0 is not exactly a nice number for us. It's going to be a problem, but normally what we would do is we would evaluate this at 3 and 0 and take ln 3, ln of 0, which of course 0 is not a legal number, so we really should be starting at 1, but I'm going to just kind of leave it up there. Now, what if, so in a sense, so if I were to calculate this difference, it would give me the upper bound of the discrete sum. If I wanted to know the lower bound sum, all I would need to do, how would I find the lower bound using the integral? Well, I would notice that this rectangle at 1 is 1, and here the continuous is at 1, but then it's a little bit less. So this one is a little bit less than that one. So therefore, if I compare this part to this, it's less. If I compare this part to this, it's less. And this part to this, it's less. So therefore, we could say that our function also has a lower bound, which is the integral of 1 over x dx from what to what? From 1, remember, I can't go from 1 to 1. 1 to 1 is no area, because from 1 to 1 there is no area because there's no width. So 1 to 2 gives me 1. To 3 gives me 2. I have to go to 4. So 1 to 4 is the area under the curve here. See what I'm shading here? Everything underneath that squiggly line is the area from 1 to 4. And what I'm saying is that area is less than the area of this plus this plus this. Do you agree with that?
Yes.
Because this is bigger than this. And this is bigger than this. and this is bigger than this. So all three pieces are bigger, therefore the continuous one, starting at 1, is smaller. It's less than or equal to. Of course, in this case, you can clearly see that it's less than, not equal to, but it's less than. But clearly, this is a lower bound. So, again, this is a discrete summation of terms, but this is an integral. So it's a different technique to solve it. This is going to be 1 over 1 plus 1 over 2 plus 1 over 3. But this one is continuous, so there's no, we don't know what the terms are. We're just going to find the integral, and the integral is natural log of x. So this value here, the solution is also natural log of x, but this time it goes between 4 to 1. This one, when we evaluate this from 4 to 1, it's going to be the natural log of 4 minus the natural log
1.
of 1. What's the natural log of 1?
0.
Yeah, e to what power is 1? 0. So this is 0, so this is the natural log of 4. So what we're saying is the natural log of 4, which is 3 to what power is equal to 2.e, what 2.71828 to what power is equal to 4? Well, it's going to be something like 1.5, 1.6. That is the area under the curve, of the continuous curve, from here to here, and that's less than boom, boom, boom. Okay? So, what does the letter sigma mean? Why sigma? Sigma stands for sum, summation, sum, adding terms. This is an integral. The integral is derived from the letter S, sum. So sigma and the integral are doing the same thing. This is summing individual discrete terms, and this is finding the continuous area under the curve. This can be an approximation, this can be an accurate value. And we can use the continuous integral as an upper bound as well as a lower bound for a discrete summation that we cannot easily solve. If we can solve a summation, we can solve it and use it. But if we're stuck, like with 1 over x, 1 over x is a special kind of series. Anybody know what it's called? So if we have 1 over n, okay? Let's say we have the summation say 1 over I, as I goes from, let's say, 1 to, let's say, infinity. That's an infinite number of terms. So we're going to have 1 plus 1/2, just like before, right? Plus 1/3, plus 1/4. What are the terms doing?
Decreasing.
The terms are decreasing. For example, one term down the line, eventually it's going to be 1 over 1 million, right? 1 over 1,000,001. But this sum, basically, keeps growing and growing and growing because it's always adding more to it, and actually this sum goes to infinity. The harmonic series goes to infinity. Even though the terms are decreasing, the sum is growing by slightly, and it will get to every number you can come up with. It will get to every number eventually. So therefore, the sum of this discrete harmonic series is equal to infinity. Harmonic series is this one, 1 over I. The integral of the function 1 over x, which is the continuous analog of the discrete, has a solution which is ln x. Ln x is by definition equal to integral of 1 over x dx. Okay, so the integral of 1 over x dx is ln x. Now, if we take the derivative of the function natural log of x, that is 1 over x. How many people are familiar, have done derivatives of functions? Derivatives. What is a derivative? Can somebody tell me what a derivative is? Let's go. Okay. So if you look at this function right here, you see this function right here? That's ln x, right? The derivative graphically gives us the function of the tangent line at a point. So for example, d dx simply means derivative. And derivative means slope of the tangent line. So the derivative of this function is 1 over x. What does it mean? It means that if I touch this line, for example, over here, so if I have a tangent line, you see what the tangent lines are doing? Are they increasing in slope or decreasing in slope? They're what? Decreasing in slope, okay. So when x is equal to 5 up here, what's the slope of this line? What's x? 1/5. When x is 10, what's the slope of this line? 1/10. So the derivative gives us the function which is the slope of the tangent line at that point. That's what the derivative gives us. So the derivative of log of x is 1 over x. And the integral of 1 over x dx is log of x. So we can call these are what operators? They're inverse operators. They're inverse operators. Okay. So we're going to do a little more than that later, but that's the idea here. So y is equal to natural log of x. If we have this function, this is true if and only if e to the y is equal to x. So natural log of x is asking e to what power is equal to x. E to the y power is equal to x. And if we have a log, so ln means log base e. What's the value of e? About 2.7? 1828, 2.7 is good enough. So if y is equal to log b of x, that asks the question, b to what power is equal to x? It's equal to y if b to the y is equal to x. All right, we'll come back to that. Let's take a look at logarithmic functions because they're very, very important for us, for algorithms. So we have a function log b. Log b, all logarithmic functions are what we call strictly increasing. And strictly increasing means that if x is to the right of another number, the log of that will be bigger than the one to the left of it. Strictly increasing. As you go to the right, the function is getting higher. That's what strictly increasing means. Strictly decreasing means that as you go to the right, the function is getting smaller. It's falling. Okay? So strictly increasing. Log b is strictly increasing. It is. And that's defined if x1 is bigger than x2, then log of any base, x1 must be bigger than the log of the same base, x2. Because x1 is bigger than x2, the log of x1 is bigger than the log of x2. Okay. Log b is what we call a one-to-one function. A one-to-one function says if x1 is not equal to x2, then the logs of x1 and x2 are different. It means that we do not have the same value for two particular x's. That's called a one-to-one function. How about y is equal to x squared? Is that a one-to-one function? Y is equal to x squared. It's not a one-to-one function because 2 and negative 2 both give you 4. And they're not equal to each other. So basically we have f of negative 2 and f of 2 is equal to 4. And so that is not a one-to-one function. But log is, because log is strictly increasing. Notice that y is equal to x squared. First it's decreasing and then it's increasing. So therefore it's decreasing, it hits every point. And then it's increasing, it hits the same y values again. So that's going to be not a one-to-one function. By definition, the log b of 1 is equal to 0 because b to the 0 is equal to 1. So log of any base of 1 is equal to 0. Okay? Log b of b to the a is equal to a because b to what power is equal to b to the a? A. B to what power is b to the a? A. Okay. If you can answer that question, then you get it. Okay. Okay. And also log base 2 of 2 to the n. Same reason, right? Also note that log 2 of 2 to the n. Now, when we have a log of something which is an exponential, that n can come out as a factor in front. So log of any base 2 to the n is simply n times log 2 of that base. And what's log 2 of 2? 2 to what power is 2? 1. So n times 1 is n, n. So you get n here. From taking this power out, you get n here as well. Okay. The log of a product, the log of x1 times x2 is the sum of the logs of each of the factors. So, for example, the log of 8 times 16 is the log of 2 of 8, which is 3, plus the log 2 of 16, which is 4. 3 plus 4 is 7. So the log of a product is equal to the sum of the logs of the factors. The log of a quotient is the difference of the log of the numerator minus the log of the denominator. So log 2 of 1024 over 8 will be log 2 of 1024, which is 10 minus log 2 of 8, which is 3. 10 minus 3 is 7. I'm using nice numbers so that you see, so some of you don't think 1024 is a nice number, but it's still a nice number. 2 to the 10th, you got to know it, right? If you're a computer science major, you don't know it's 1024, maybe you should consider a different major. All right. That's called a K, right? All right. Rules of logs, continuing. So let's say this is what we were talking about before. If you have a log of an exponential, the exponent can come out as a factor. So this a can become a factor, and we just have log b of x. Okay? So as an example, log base 4 of x cubed is 3 times log 4 of x. Stop me if any of this is confusing. Okay, log 4 of 64 to the third is 3 times log 4 of 64. 4 to what power is 64? 4 to what power? 4 times 4 is 16, 4 times 16 is 64, 3. So 4 to the third power is 64, so this whole thing is a 3 times 3 makes 9. Oops. Okay, so here is a very important rule for us will be the change base rule. The change base rule says log b 1. That means one base. Could be 2, 3, 4, 5, e, whatever. The log of one base of x is equal to the log another base of the same x, as long as you divide by log of the second base of the first base. So let me show you what that means, and that's important for us. That'll be important for us to show. And it also has some important implications in terms of how logs relate to each other. So what I'm saying here is log base 2 of 8 is equal to what? 3, right? Is equal to log, if I don't put anything by the base, what base is it? 10. Log base 10 of 8 divided by log base 10 of 2. I'll do another one. So if we have log base 2 of e, that's going to equal to the natural log of e over the natural log of 2. Change base. So what's the natural log of e? So this is equal to 1, so this is going to be 1 over natural log of 2. So log of one base can be translated to log of another base. Okay, so if you look at this, basically log 2, so if you take this example here, and you say this is equal to this, times log 1 over log b of b1. Right? b2, b1. So what do we call this? This is the old base, this is the new base. So therefore this is what? This is a variable, this is a variable, this is a what? It's a constant. Constant. So for example, if b1 is equal to 2, if b1 is equal to 2, and b2 is equal to, let's say, 6, then the denominator, these are the same. The base changes, they're the same. But the denominator is log base 6 of 2. That's a constant. To what power do I raise 6 to make 2? I don't know, some fraction, right? Some fraction. So therefore, log of base 1 of x is equal to log base 2 of x with a multiplication of a constant, which is the log of the second base of the first base. That's a constant. So that should give you a clue that all logs are related to each other and they are proportional to each other. What do I mean by proportional? What are proportional? What does that mean? If two functions are proportional to each other, what does that mean?
It is a multiple of.
It's a multiple. You can go from the one function, there is a multiple, like 2. If you take the first function multiplied by 2, you get the second function. So the first function is 3, it's 6. The first function is 35, it's 70. If it's 150, it's 300, because the constant is 2. There's a constant of proportionality. The constant of proportionality could be 1, 2, 1.5, 1.6, 1.7, 1/2.
Any.
Okay, so functions, and this is important, so functions that are proportional to each other
Have a constant.
will have a constant between them, but how do they grow? They grow, how do they grow? Functions that are proportional to each other. They're growing what? Imagine a function and then imagine a proportional function and let them go to infinity. How are they growing? Parallelly. That's an interesting way of putting it. They are growing, let's just say similarly. They have similar characteristics, right? For example, let's say a function y is equal to x squared. Can you imagine that function y is equal to x squared? Parabola, y is equal to x squared. Now forget about the left side, just look at 0. Oh, here. Now think of the function y is equal to 2x squared. Forget the left side. What's this function going to look like? This is the original function. What's the new function going to look like? Similar, but a little quicker, right? A little more stretched. So similar. So is x squared and 2x squared, are they proportional to each other? Yeah, and the proportionality factor is 2. Because x squared gives you, when x is 10, x squared gives you 100. But 2x squared gives you 200. X squared for 11 gives you 121. But 2x squared gives you 242. Get it? So proportional. So functions that are proportional to each other have similar looks. They have a similar growth. Yes, the one with the bigger coefficient will grow a little more quickly, but they are proportional to each other, which means that their growth rate really is the same. That's why when we analyzed bubble sort and we got one function was 3.5 n squared, another one was 2.5 n squared, we realized that one of 2.5 was a little bit better, but proportionally, as the limit of these functions goes to infinity, we see that they are really the same quadratic complexity. They're doing the same thing. Neither one of them has a lower level of complexity, although it could have faster performance, a little fewer instructions, but not much. If one is in the billions, the other one's in the billions. If one is in the trillions, the other one is in the trillions. Okay, so they are proportional. Maybe less trillions, but still trillions. Maybe less billions, but still billions, etc. Okay, let's look at this function right here. And so here we have a to the power of log b of x and x to the power of log b of a. These two are actually equal to each other, and we can find out that they're equal to each other by taking the logarithm of both sides. If we take the log b of this, we get log b of this equals log b of that. But then this exponent can be used as a factor. So this log b of x comes out in front, and this log b of a comes out in front. And so what we have is log bx, log ba, log ba, log bx. These are the same. So these two, so the a and the x can be exchanged and have the same expression. Okay, let's talk about our summations. So summations are going to be extremely important for us because all our algorithms, we're going to basically end up getting summations or recurrences. So this one we already saw how it works, and it's a pretty straightforward solution. You see it's n times n plus 1 over 2. We talked about this one already. This one is the summation of I squared. So what we're doing is we're adding 1 squared, 2 squared, 3 squared, all the way to n squared. And the solution is here. We're going to go over that solution and how to solve that summation. The next one is an exponential summation. Summation I goes from 0 to k of 2 to the I, and we add 2 to the 0, 2 to the 1, 2 to the 2. How many terms are in this summation? K plus 1. Why plus 1? Because we're starting at 0 and then 1. So it's k plus 1. So you can see that the first term is 2 to the 0, which is 1, 2 to the 1, which is 2, and the last term is going to be 2 to the k. The solution is going to be 2 to the k minus 2 to the k plus 1 minus 1. Does anybody know what kind of series that's called? Geometric series. And who can tell me what a geometric series is?
You get the next number by multiplying.
So we can get, if this number is 2, this number is 4. The next number is 8, next number is? So if I know one number, all I need to do is, all I have to know is the ratio of the series to compute the next one. The ratio in this case is 2. But we could have, for example, a ratio could be 3. For example, we could have the summation as I goes from 1 to 5 of 3 to the I, and that's going to give me 3 to the 1 plus 3 to the 2, all the way to 3 to the 5. Right? So is that a geometric series also? Well, let's see. This term is 3. Then we have, this is basically this times 3, so that's a ratio of 3, right? This is this times 3, so the ratio is equal to 3. So if I give you any term, multiply by 3, you get the next term. If I divide it by 3, I can get the previous term. Okay, so that's called a geometric series. A geometric series requires the ratio. If you want to make sure there's a ratio, test it once on first to second, second to third. Make sure the ratio continues for at least the first 4 terms before you say it's a geometric ratio, because some of them look like geometric series, but they're not. For example, a common mistake is people think that a harmonic series is a geometric series. But remember, a geometric series has a solution, but a harmonic series does not have a closed form solution. That's why we have to use the integral to squeeze it from the top and the bottom. So the next very important summation is a summation I 2 to the I. So basically what's happening is it's a summation of products. Product, 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 product. How many terms? Okay. If I change the I to 0, would that make any difference? Why not? Because I times 2 to the I would be 0 for the first term, so it wouldn't. So it doesn't make any difference. Okay, so notice that for each of the factors, I is growing in a linear way. 1, 2, 3, 4, all the way to k. But 2, which is the other product, is growing how? 2, 4, 8, 16 is growing exponentially. So this is not a geometric series. And how can you, if I said prove it's not a geometric series, how can you prove it to me? Well, all you need to do is you need to say, hey, the first term here is going to be 1 times 2 to the 1. That's what? That's 2. The next term is going to be what? 8. Now, if this is a geometric series, the ratio has to be what? Would have to be 4, which means the next term would have to be 32. But actually it's what?
24.
27.
24, right? Yeah. 24. So therefore the ratio here is 4, but the ratio here is 3. No. Not a geometric series. So we cannot use this simple solution for it. Okay, the solution is here, and I will show you how to get that also. We'll do that today. Okay, so we need to know how to solve these and other types of summations. So let's take a look at the summation. This is a summation of I, as I goes from 1 to n. So you can see over here, the way we're going to solve it, we're going to do something a little strange. So we're going to try to, this is what we're trying to solve. We need a closed form, right? We already know the answer is going to be n times n plus 1 over 2. But we're going to show you a technique that's going to be useful for you. So what we're going to say is, we're going to say we are going to look at, even though we're looking to get I, we're going to find I squared. And we're going to set summation of I squared equal to summation of I plus 1 squared. Now, the only way I can, so if you want I to the first power, set two equalities of I to the second power. So this is the second power, this is also a second power, but this is I plus 1. Now watch very carefully, because this is where it gets tricky. In order for this summation to be equal to the other summation, they both have to have the same terms. So what? Give me the first three terms of this summation on the left. 1,
4, 9.
2, oh, sorry, 1,
4, 9.
4,
9.
and 9. 1, 4, 9. Okay, now, what's the last term going to be? N squared. Okay, now, here what we have is I plus 1 is 1. So when I plus 1 is 1, what's the value of the first term? When I plus 1 is 2, what's the value? When I plus 1 is 3, what's the value? And when I plus 1 is n, what's the value? Okay, so you see that they're still the same terms, right? Now, what we can do is we make a change. We actually did two things here, which I kind of hate when I do that, but I did it, so I'll show you. You understand, you understand I plus 1 squared is this, right? Okay. So I didn't change anything in here, I just multiplied. Now here, what I did was, I did what? I subtracted 1 from here, right? So I subtracted 1 from here, this is I. And what did I do here? Subtracted and subtracted. Okay, so now let's make sure, so what, when the value of I is equal to 0, what's the first term? 1. When I is equal to 1, what's the value?
4.
1. 1 squared plus 2 is 3. 4. How about when I is equal to 2? 4, 8, 9. Get it? So you understand this is equal to this, but this is also equal to this. Okay, everybody understand this beginning? Okay, so, and you'll see this because we're going to do this again for a more complicated summation. So trying to solve I solve I squared. Now, now I'll show you what I'm going to do, and then I'm going to show you why we did this I squared. Because it sounds crazy. Why would you want to make it I squared when you're trying to solve I to the first power? Okay, so first of all, what I'm going to do is I'm going to do the following. I'm going to say this summation of 3 terms is equal to, we're going to expand it, leave this here, subtract this, leaves what on this side? This minus this is 0. Do you see that? Again, this is equal to, these two are equal, right? This, take away this, is equal to 0. Okay. Now, the summation of 3 terms, the summation of this plus this plus this is the summation of this plus the summation of this plus the summation of this. So that the summation can be distributed. Look at the indexes. 0 to n minus 1. Notice that this is 0 to n minus 1. I changed the notation a little bit, but it's still the same index. So the summation of 3 terms is the sum of 3 summations. So it's going to be sum plus sum plus sum minus sum equals 0. Now watch. Now I'll show you why I'm doing the squares. What I'm going to do is notice here that I have, this is positive I squares. Right? But this is positive I squares, but they're being subtracted. So what do you think the I squares are going to tend to do? Cancel. And that's why what I did here is I added I plus 1 here, so I could cancel the quadratic i's, which are here and here, and be left with the linear stuff for the solution. So my goal is going to be to cancel this one as much as I can with this one. But they're a little bit different. even though the summand inside is the same, the indexes are different. This one has a 0, this one doesn't have a 0. But actually, the 0 doesn't matter, does it? Because what's 0 squared? So that means 0 squared is going to be nothing, right? That's down here. This one has an n minus 1, this one has an n minus 1, but this one has an extra n. So when I is equal to n, this is minus
N squared.
n squared. You see it over here? So this is the leftover from here, and this is the leftover from here. Everything else
Cancel.
canceled. So what we have here is this canceled with this, leaving these two pieces. These are the cancellations. So now what I have is I have to compute these summations. These summations. So this is a summation as I goes from 0 to n minus 1 of 1. That means 1 plus 1 plus 1 plus 1 plus 1. How many times? N times. That's the n. And then I am left with the summation from 0 to n minus 1 of 2i. Now, when you have a summation, and one of the factors is a constant, that constant can actually come out
Come
here.
on.
When the constant comes out here, we have 2 times whatever is the sum of I. Well, sum of I is going to be n minus 1 times n over 2 times 2. It's going to cancel. Okay? So what we're going to have is we're going to end up with having, let's go up a little bit higher. So what we'll end up having is these are going to cancel, so we're going to have this summation plus n minus n squared. And then I'm moving it over here, so it's n squared minus n is equal to n times n minus 2. And this is equal to 2 times the summation of I. So now all I need to do is divide by 2, and I get the summation of I is equal to n times n minus 1 over 2. Now, now what I want is I want the summation from 0 to n, so I can replace n with n plus 1. When I replace n with n plus 1, I get n plus 1 minus 1 is n of I, and then I can say n with n plus 1 is n plus 1, and n plus 1 minus 1 is n over 2. So here's our summation. Okay, any questions?
Sorry, how do you get a minus n squared again?
This one right here?
Yeah.
Okay, so Drake, if you look at this summation here, and then you look at this summation here, notice that this is I just moved this one from here to here. I changed it, right? So to put them close to each other. So basically, if you look at these two summations, this one is adding whatever this one is subtracting, except that this, when I is equal to n, is not here. So when I is equal to n, this is a separate term only here. So it's going to be n squared. Notice that I squared is the same. So when I is equal to 1, 2, 3, 4, 5, 6, 7, all the way to n minus 1, they both have 1 to n minus 1, 1 to n minus 1. So they will just cancel. This one has an extra 0, but the 0 produces nothing. This one has an extra n, and the n produces this one. Why is it minus? Because the whole sum is being minus, 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 minus. Okay? Okay, good.
Professor?
Yeah.
How you're changing those bases, like I is equal to 1 and I is equal to 0 to n. and
Hold
n
on a
minus
second, I'm
1.
sorry.
Yeah, at one. Even in the beginning, you changed it to the I is equal to 1 to n, like summation.
Here.
And how can you make it to the 0? Because it's like, I don't understand.
Okay, so let's think about it this way. Okay, that's a very good question. It's a very good question.
Yeah.
You can always change something if it doesn't change anything in the term. So, if you look at, you understand why I made I plus 1 here. I use I plus 1 here because I plus 1 could go from 1 to n, and that matches 1 to n. Okay, but then your question is, how can I go from 0 here? Okay, so basically, think of it this way. The first value for I plus 1 is what? The first value for I plus 1 is what?
1.
is equal to 1. That means that I is equal to 0. And it's increasing by 1. The last value of I plus 1 is n, right? I plus 1 is equal to n. So that means the value of I is actually equal to n minus 1. That's how I can do it. Does that make sense? Not so much, right? What I'm saying is this. I'm going to trip over. What I'm saying is, if I plus 1 is equal to 1, that means I is 0.
Yeah.
So I kind of didn't change anything here.
For this particular equation, you can do that, but not every time, maybe.
You can do it every time as long. The reason it looks weird is because I have a weird index. I plus 1 is a weird index. But basically, say to yourself, what if I plus 1 is 1? What's I? I has to be 0. That's why I can do it. Okay.
Can you start with -1? So, for example, is there an equation that starts like -1 less than I less than n?
-1. Where?
I mean, is there? Can you? Right now, no. We can start from 1 or 2 or.
You talk about here?
Yeah. Can you ever start with negative?
Well, you could, except that we're trying to find this solution, so we want the index to go from 1 to n, so our index, which is I plus 1, is going from 1 to n. We're matching it. If this one is going from -1 to n, but remember, the formula is for the sum of integers. If you're going to -1, -1, 2 is what? Then you got a little, I have to think about it. It's not typical. You're not going to use it typically. Okay, let's look at another example very similar. So now that you're going to get the idea, so what we're trying to do is we're trying to solve I squared, so we're going to set it up with I cubed. So we're going to get a cube here, and then we're going to bring this over here, so it's going to be negative. And then this will be 0. See? Negative, and this is 0. So what we're going to do is this is going to produce cubes, and it's going to produce negative cubes. The cubes will cancel out. We'll be left with squares. Because we have to have a difference. We have to somehow separate it. So you can see from here 1 to n. Now we have 1 to n is I plus 1. And the same deal. If I plus 1 is equal to 1, then I is 0. If I plus 1 is equal to n, then I is n minus 1. So I didn't change anything here. I just made this right here. So basically all I do is -1, -1, -1. Subtracted everything from the variables. Now, what is this? This is nothing more than I plus 1 times I plus 1 times I plus 1. So how many terms do I have? 4. So the summation of 4 terms will be 4 summations. So it'll be this summation, plus this summation, plus this summation, plus this summation. And here they are. 1, 2, 3, 4 become 1, 2, 3, 4. And then we're subtracting this one, setting it equal to 0. So again, the idea is we want the cubes, which are negative, to cancel with the cubes, which are positive. And again, Drake, you can see that this is 0 to n minus 1. 0 is nothing. So just think of it 1 to n minus 1. And this is 1 to n. So there's that extra n in here, and we're subtracting it. And that's why there is going to be a minus n cubed. You see? When you see it the second time, it's like, okay, it was not so evil. All right. So what we have is, so the summation is going to be I, summation of cubed, summation of 3I squared. By the way, the 3 can come out to the front, right? And we already have a solution for I squared. Well, actually, we're going to solve that. We're going to do in a minute. And then, but we have a solution. This is going to be 3 of this, and the summation of that. Minus that is equal to 0. So what I did was I kind of changed the order. I brought this one forward so you can see these guys over here. And so therefore 0 is coming from here, and subtracting n cubed is coming from there. And then you understand why this is n, right? 1, 1, 1, 1, 1, 1, 1, n times. This is 3 times summation from 0 to n minus 1 of I, which is going to be n times n minus 1 over 2 times 3. And then finally, this one is just going to be 3 times I squared, which is what we're trying to solve for. So what we're going to do is we're going to take everything is going to, this is going to stay here, and everything else is going to go on that side over here. So we're going to get 3 times the I squared is going to be equal to all this stuff here. And since we're interested in I squared only, we'll divide everything by 3. When we divide it by 3, put it in the common denominator, we get this. But that gives us the summation of I squared from 0 to n minus 1. We're interested from 0 or from 1 to n. So how do I do that? I replace this with, I replace n with n plus 1, because if n is n plus 1, n plus 1 minus 1 is n, and this is going to be n plus 1 cubed minus 3 times n plus 1 squared plus n plus 1. So when I do that bit of algebra, when I do this out, I get the summation from 1 to n, which is the same as 0 to n, because 0 doesn't add anything. And that equals to this very important result, which you write down on a sheet before the midterm exam so that you have the result, because I certainly don't want to have you do this from the beginning. But I want you to find algorithms where this is going to be useful, and then you're going to be able to solve it. Okay. Now, let's look at the geometric series. So the geometric series is a series that has a ratio of terms. That ratio has to be some number which is going to be usually greater than 0, less than 1, or greater than 1. So it could be more than 1, it could be less than 1. But it's some positive number, not equal to 1. If it's equal to 1, then the terms just repeat. Okay, so in this example here, so what we have is, the summation here is 2 to the I, as I goes from 0 to k, so it's 2 to the 0, 2 to the 1, 2 to the 2, tick, 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 all the way 2 to the k. So we can see that each term is double the previous one. 1, 2, 4, 8, etc. So our summation is going to be computed in the following way. The summation of the n geometric terms is a, where a is the first term. That's 1. A is equal to 1. R, which is the ratio, it's equal to, in our case, to 2. And n, which is the number of terms. The number of terms, well, how many terms do we have? 2 to the 1 through k is k plus 1. So we have k plus 1 terms, ratio is 2, first term is 1. So all we need to do is we need to plug it into the formula. So it's going to be first term minus first term times r to the n minus 1 minus r. So it's going to be 1 minus 1 times the ratio to the n over 1 minus r. That gives me 2 to the k plus 1 minus 1 over 2 minus 1 when I multiply both sides by negative, top and bottom by negative 1 over negative 1. Does that make sense? Let's look at another simple example. So I'll give you a simple example that's going to be useful to you. Let's compute a geometric sum. First of all, let's make sure it's geometric. I think that's going to be helpful. Okay, so let's take summation as I goes from 0 to 4 of 1/2 to the I. Okay, what's the first term? Well, just write 1/2 to the 0, right? Plus 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3 plus 1/2 to the 4. Okay. What is this? 1 plus 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 plus. Okay, is this a geometric series?
Yes.
If it is, then basically the ratio from here has to be 1/2, half of a half, quarter, half a quarter, half, okay, geometric series. So what's the first term? So A is equal to 1. What is the ratio? 1/2. And what is the number of terms? Well, 1, 2, 3, 4, 5. So n is equal to 5. So according to our formula, we're going to have A, which is going to be 1 minus 1 times the ratio to the power of terms over 1 minus the ratio. So we're going to have 1 minus 1/32, right? 1 minus 1/32 over 1 over 2. So 1 minus 1/32 is what? 31 over 32 times 2 over 1. So it's going to be 31 over 16. If you don't believe me, you can check it manually. I know it's not a lot of work, but it's a kind of a pain. That's the solution.
Sorry, how do you get an A again?
A is just the first term. So let me show you a slight modification. So let's say you wanted to find out what is the summation as I goes from, you ready for this? Let's go from, I goes from 1 to infinity of 1/2 to the I. Now how many terms is that? An infinite number of terms. So basically what you do is you can replace infinity with n and take the limit of the summation as n goes to. You see what I'm saying? So let's not worry about the limit until we solve the summation. So what we're going to do is we're going to determine, what's the first term? 1.
No.
1 over 2, okay. So A is equal to 1/2. What's the ratio? 1/2. And what's the number of terms? N. So we're going to have 1/2 minus A times the ratio to the number of terms over 1 minus the ratio. Okay. So we're going to get 1/2 minus 1/2 to the n plus 1 over 1/2. Correct? But remember, we're taking the limit of this as n goes to infinity. The limit as n goes to infinity, what happens to this as limit as n goes to infinity? 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 forever. It goes to?
0.
So what does the sum go to?
1.
So even though we have an infinite number of terms, the sum converges to 1. Okay, what if I change this from a 1 to a 0? How did you know that? Are you a genius? No, because 0 is 1/2 to 0 is 1. It would just be 1 more than that 1, so it has to be 2. So the actually would be 2. And what would change here is that the A would be equal to 1. So this would be 1. This would be 1, 1/2 to the n. This would still go to 0, so it would be 1 over 1/2, which is 2. Okay, so let me give you one more example of the geometric series. What if I wanted you to say the summation as I goes from, let's say, 4 to 7 of 1/3 to the I? Okay, so is this a geometric series? Yes. What's the first term? First term is going to be 181. And what's the ratio? And how many terms?
6.
Now, the problem is we can't solve this equation. We cannot solve this equation using our formula. Why? Because the formula basically says this is how to find the geometric equation from 0 to k. And we don't have a 0 on the bottom. So what we have to do is we have to say this is equal to summation as I goes from 0 to 7 of 1/3 to the I, meaning we're going to add the terms 3, 2, 1, 0, and then we're going to subtract the terms 3, 2, 1, 0. Does that make sense? So we're going to say the summation of terms 4, 5, 6, 7 is equal to 0 through 7 minus 0 through 3, which leaves 4, 5, 6, 7. So that can be solved this is going to be 1 minus 1 times the ratio to what? What's the number of terms? 8. Good. Over 1 minus 1/3. Minus, what's the first term here? 1 minus 1 times 1/3 to the 4 over 1 minus 1/3. So this is 1 minus what? That's a big one. I'm not going to bother doing it. But it's doable, right? It's doable. 3 to the 8th power. Wow. That's going to be very, very small. You can see when the ratio r is close to 0, it's a number between 0 and 1, you can see that for a large number of terms, that term disappears. This is almost going to disappear. You understand what I'm saying? I mean, 3 to the 8th power. Anybody got it handy? 6,500? Yeah. So this is going to be so small, right? 1 over 6,500, something like that. So it's basically, so what's 1 minus 1/3? 2/3. So this is close to 1 over 2/3, which is equal to what? 3 over 2? Now this one is a little bit, what?
81.
Yeah, so this is going to be 1 minus 1 over 81 over, same thing, 2/3, right? So this is going to be 80 over 81 times 3 over 2. So it's going to be a little bit smaller. Anyway, that's how you would solve it. Okay? So geometric series. The ratio can be a positive integer. It could be a real number integer, real number positive, or it could be a number between 0 and 1. In our cases. All right. This, what time am I supposed to? Okay, let me just do this one real quick. We started a little bit late, that's my fault. So I'm going to punish you for having to stay extra long. Okay, so what we want to do is we want to solve this. This summation is a very important summation for us. That's why I want to keep you here. So we want to solve I 2 to the I. This is not a geometric series, we already know that. So I kind of gave you a clue last time how we're going to solve this one. What we need to do is kind of what we did before. When we wanted to solve I or I squared, we wanted to get a couple of them and do a subtraction so they could cancel each other. Sometimes when we solve a summation, we call this a telescope. You know what a telescope looks like? You make it longer and longer and longer, and whoop, everything cancels out when you push them together. So we're going to create a telescope in this. So to do that, we'll recognize that I 2 to the I is equal to I times, instead of 2 to the I, we can rewrite this like this. Double it and subtract half of it is original. Now, do you understand that 2i plus 1 minus 2i is the same as 2i? Right? 512 is the same as 2 times 512 minus 512. Because that's the way powers of 2 work. Okay, so now why do we do it? We did it because one gives us a positive series and the other one gives us a negative series. So what we have is by doing that from I to k, we have sum of I 2 to the I plus 1 minus sum of I 2 to the I. And so that's exactly what we have right here, right? Not too difficult. Now the beautiful thing is that we have something that looks quite similar, plus and minus. The bad thing is they're not the same. You can't just subtract them because they're not the same. The terms are different. So therefore what we're going to do, we're going to play a little game. Okay, you're going to like this one. You're going to like this game. This is a different game. This is a game of changing the index. If you change the index, if the index is 1 and you use it here, it's equal to 1. When index is 2, it's equal to 2. So if I change the index from 1 to 0, I have to add 1 to the use to make the term the same. So if you move the index away from what they used to be, you have to up their use. If you move the index up from what they used to be, you have to decrease the use. So that the terms are always the same. That's the test. Are the terms still the same? So look what we're going to do. So everybody understands this part, right? This minus this. Now, what I'm doing is, right here, is I'm going to move this index down to 0. and this index down to k minus 1. So I'm moving the index down by 1, so therefore initially when the index was 1, this was 1, 2 to the 1. So when it's 0, it has to be I plus 1. That's going to bring it back to 1, and this has to be I plus 1. So the question is, why the heck did I move the index down? I moved the index down so that I can more perfectly match 2 to the I plus 1 and 2 to the I plus 1. Unfortunately, it makes another two summations here, right? It's going to be minus this summation minus that summation. So when I distribute this I to here, or this 2i plus 1 here and here, I get minus, notice the indexes are 0k, 0k minus 1. I get minus this, minus that. Does everybody see that? And now what we have is we have a telescope. We have I 2 to the I plus 1, I 2 to the I plus 1. One is positive, the other one is negative. They don't have the same terms, but almost. In fact, notice this one has a k, this one doesn't. This one has a 0, this one doesn't. So this summation will contribute one term. And the term will be when I is equal to k. When I is equal to k, this is k times 2 to the k plus 1. That's the remaining term, the highest term in the summation. This one will only add one term. That's a term when I is equal to 0. But when I is equal to 0, it's 0 times this. So this term doesn't exist. It's just 0. So the telescope cancels everything except this one. So now what we have is these two have telescoped together, leaving this. Okay? And then what I did was I went crazy here. I gave you basically, when I pull a term out, I go 1 to k minus 1 and 1 to k minus 1. So that's a telescope. Right? And that's a 0 from here. And then I have minus this. But this is just a geometric series. So what I have is I have k times 2 to the k plus 1, cancel, cancel, 0, minus 0 to k minus 1 geometric series. And this geometric series is simply nothing more than 1 minus 1 to the 2 to the power of k over 1 minus 2, which is 2 to the k plus 1 minus 2. So when you take this, that's the value of the summation from 1 to k. So the summation 1 to k is going to be now. Of course, here we have k times 2 to the k plus 1 minus 1 times 2 to the k plus 1. So it's really k minus 1 times 2 to the k plus 1. Everybody understand that? So this is k of them. This is minus 1 of them. So it's k minus 1 of them. Plus 2. So that's the summation. So as an example, and I know that we're going to be leaving momentarily, so if I have the summation, for example here, summation as I goes from, let's say, 1 to 5, I 2 to the I, that's going to equal what? Let's find that closed form for that. So it's going to be 5 minus 1 is going to be 4 times 2 to the power of 6 plus 2. What's 2 to the 6? 64. 256. This is equal to 258. Okay? That's it. And just in case you wanted to try this at home, and nobody's looking, and I'm not going to do it, I actually have one more that I thought you'd find fun. I'm not going to do it. This one is a little trickier, but it's the same thing. Still the telescope. The problem here is that 3 to the I is equal to 3 to the I plus 1, but you have to take 2 of 3 to the I, because it's 3 times that. This is 3 times more than this, so you got to subtract twice 2 of the previous ones to make it balanced. So it makes it a little more complicated, but you still get the same telescope, everything simplified, and you have a very exciting, result. We call this, in computer science, an exciting result. Closed form is always exciting. I'm done.